Hi everybody. Today I'm going to talk to you guys about standing waves. Standing waves are cool, and you probably already made some of them when you had the Slinkies. So the question for you is, how do they work? How does a standing wave work? And standing waves really are waves that look like they're standing still, even though they're actually moving like normal. They happen in certain situations, and those situations are the situations similar to what you're going to see here in my diagram. So let's take a very simple case, and that simple case is waves on a rope. So here I have drawn a rope, and we're going to be looking at waves that are generated and then sent along that rope. What you find, if you tie one end of the rope to a fixed point, like a stand or a wall or something, and then you tie the other part to a mechanical oscillator, something that you can set at a certain frequency, and it produces waves by pushing the arm up and pulling it back down again, which in essence does work on the rope. What you find is that there are certain frequencies where weird things happen. And so we're going to talk about that here real quick. So first, if I just send out a wave pulse like so, by moving the arm up and down here, you're going to get a wave that looks like this, and then the rest of the medium, right? So you have a wave, that's a little bit hard to see, I apologize. So, and like so. You get a wave that looks like that, and then that moves along and then hits the wall. Now what happens when it hits the wall? It's a fixed point. When it hits the wall, it's going to reflect back. Now you might remember that when a wave reflects back, it is 180 degrees out of phase. What that means is it's flipped over, right? So for transverse waves, it's flipped over. So that means if this is a crest and this is a trough, when it gets turned around, you're going to end up with a crest here and a trough there, like so. So as it goes down, it's going to hit that wall. It's going to reflect 180 degrees out of phase. Now, if you notice, when these two waves hit each other, let's say a second wave was produced, after a delay, a second wave was produced. When these two waves hit each other, when the trough and the trough coincide, they're going to make a bigger trough, right? Because of interference. Interference says you need to add the amplitudes of the waves together. So for that one bit of time in the middle here, when these coincide, it'll look like this. So there's the crests of each, but then the trough will be down below, like so, because of interference. Technically, it's also called superposition, which means the two waves are in the same place, positioned on top of each other. So it'll look like that. However, they'll continue to move. This wave will continue to move this way, and this wave will continue to move that way until the troughs have passed, and the crests are what's built up. And so after a brief moment, you're going to end up with something that looks more like this, where you have a trough here and a trough here, and then a very large crest there. So what you end up with is that interference, right? Constructive interference as they pass through each other. Now, if you continue to change the frequency and you continue to oscillate the arm up and down so that waves are always being generated, there is a point at which the frequency of the wave that you produce, or the waves that you produce, will cause the reflected crest, so the entire rope will be either all up or all down. So the crest that's being produced and the crest that's being reflected coincide with each other, and they build up on each other. So the trough and the trough could do the same thing, and so you might find, let's say, something like that. And so the wave itself looks like it's just oscillating up and down. So it's going all up and all down, all up and all down. And I'll show you that in just a minute. We call this a standing wave because it doesn't look like it's moving. It just looks like the wave itself is standing still, even though it is, in fact, moving this way and interacting with the wave that's being reflected that way. So it's produced by both of those things. So that's a special kind of standing wave. It's called the fundamental because it's the most basic of all, or the largest of all the standing waves, or sometimes the first harmonic. Now, you may remember the word harmonic from simple harmonic motion. You remember we talked about how it has a relationship with music, and so this should be your clue that this is going to be important for how musical instruments work, this first harmonic right here. So, all good, right? What happens if you increase the frequency? Well, if I increase the frequency on the mechanical oscillator, it ends up getting out of phase again, and so you get all sorts of wiggles and everything is fine. But it's not a standing wave anymore because you can actually see waves moving back and forth. But there's another frequency at which the rope, there's the rest position for the rope. There's another frequency at which the wave crest here that's going out and the wave crest that's coming back coincide, and the wave trough that's going out and the wave trough that's coming back coincide. And so same thing with the trough and the crest. And so we end up with a wave that looks like this, where the rope itself just bounces up and down along these 2 points. But this point right here doesn't seem to move hardly at all. And then these 2 points on the ends don't seem to move hardly at all either. And so at the end, what we have is another standing wave, because it just looks like it's oscillating back and forth like that. And we call that the second harmonic. So when you're naming harmonics, you look at the number of loops that they have. Those loops have a special name, and we're going to talk about that right now. That special name is the antinode. Right there. And right there. Antinode are like the loops. The places where they don't seem to move, like there, there, or all the way over here, are called nodes. So you've got nodes that don't seem to move, and antinodes that seem to move all over the place. Now, the cool thing about this one in particular, is that this distance is now exactly one wavelength. So if you know what the second harmonic is, what the frequency for the second harmonic is, you automatically know what the wavelength is as well. And so you can figure out what the speed of the wave is, because frequency times wavelength equals the speed of the wave. So second harmonic is kind of a nice one. You can go as many harmonics as you want. In fact, that's what musical instruments do, right? So I'll just draw a few more so you can see what that looks like. So this would be a third harmonic. This would be a fourth harmonic. This would be a fifth harmonic. And so on. I'm not going to draw the sixth one. It's getting kind of crazy over there. Interestingly, though, to produce these, you have to continue to increase the frequency. This one should have the lowest frequency, and this one should have the highest out of the ones that I drew. That makes sense, right? Because if you think about it, the speed of the wave is equal to the frequency times the wavelength. Look at the wavelength here. This distance is half of a wavelength. So the wavelength is biggest, so the frequency must be smallest, because the speed of the wave can't change. The rope can only have certain speed waves. So if the wavelength is low, the frequency must be high. If the wavelength is high, the frequency must be low. As the wavelength gets smaller, like here, this is a wave. So this is 1/2 of a wave. This is exactly one wave. So now the wavelength has gone down, the frequency must go up. Here we have one wave plus 1/2. So now we've got even a smaller wave length, which means an even higher frequency. Here we have 2 wavelengths. And so wavelength has gone down even farther, frequency must go higher. So as you go through this, you see that you need greater and greater and greater frequencies to be able to produce these harmonics. In fact, there's a relationship with the the frequencies that we'll talk about later on that you'll be able to see. The frequency that produces this harmonic and the frequency that produces that harmonic, you see they have a pretty basic relationship that we can talk about.